All right, let's get into it. We're going to talk about the invisible chemistry that's literally all around us. Acids, bases, and salts. Well, the answer to that, it all comes down to the basic chemistry of acids and bases. And trust me, they're in way more things than you probably think. So here's what we're going to cover. First, we'll figure out how to spot these chemicals in the wild. Then, we'll see what happens when they go head to head. We'll learn how to measure just how strong they are, and why that even matters in our daily lives. And to wrap it all up, we're going to uncover the secret superpowers of something you probably have in your kitchen right now: table salt. All right, first up, how do we even tell these things apart? I mean, besides the obvious. And please don't go around tasting everything. There's a much safer way. You know, the most obvious clues actually come from our senses. Acids, think about lemons or vinegar. They have that classic sour taste. And bases? Well, think about soap. It's got that bitter taste and feels super slippery when it's wet. But in a lab, the go-to test is with litmus paper. It's super simple. Acids turn it red, bases turn it blue. A really easy visual way to tell what's what. But litmus paper isn't our only tool. We've got a whole squad of chemical detectives called indicators, and their whole job is to change color, or sometimes even smell, to give us a heads up about whether we're dealing with an acid or a base. Okay, check out that second one on the list, turmeric. You have absolutely seen this in action, I promise. Have you ever spilled curry on a shirt? The moment you scrub it with soap, which is a base, that yellow stain turns this weird reddish-brown color, right? That's it. That's the turmeric acting as a natural indicator right in your laundry. Okay, so we know how to spot them. But what happens when an acid and a base actually meet? This, my friends, is where things get interesting. It's time for a chemical face-off. So first up, what happens when an acid meets a metal? Take a look at this experiment. We've got some zinc granules being dropped into a dilute acid. And see all those bubbles fizzing up? That's not just for show. That's hydrogen gas being created right before our eyes. And this is a pretty universal rule. When an acid reacts with a metal, you're almost always going to get two things: hydrogen gas and something called a salt. But the real main event is when an acid and a base finally come together. This is what we call a neutralization reaction. I mean, they're basically chemical opposites, so when they meet, their one mission is to completely cancel each other out. So what do you get when these two opposites collide? You get two of the most neutral things imaginable: a salt and good old water. And a perfect, everyday example of this? Taking an antacid for heartburn. You're literally swallowing a mild base to neutralize that extra acid in your stomach. The result? Harmless salt and water and relief. That's a neutralization reaction happening inside your own body. Okay, but it's not just about is it an acid or a base. It's also about, well, how acidic is it? Is it like lemon juice or is it like battery acid? To figure that out, we need a way to measure it. We need a scale. And that's where the pH scale comes in. This is our go-to tool for measuring strength. It's a scale that goes from 0 all the way up to 14. And fun fact, the P in pH actually comes from a German word, potens, which means power. So we're literally measuring the power of hydrogen, those little ions that give acids their kick. And we can actually see the pH scale in action with something called a universal indicator. It gives us this amazing rainbow of colors. You get these bright reds for strong acids, a nice neutral green right in the middle, and then it shifts into these deep blues and purples for the really strong bases. It's like a color-coded cheat sheet for chemical strength. So here's the simple breakdown. If the pH is less than 7, it's acidic, and the lower the number, the stronger it is. If it's exactly 7, it's neutral. Think pure water. And if it's above 7, it's basic or alkaline. The closer you get to 14, the stronger the base. Pretty straightforward. All right, a color-coded scale. That's cool. But why does this actually matter to you? Well, it turns out this little scale has a huge, huge impact on pretty much everything: our bodies, our health, and the entire world around us. I mean, just think about it. Your own blood has to stay within this tiny, precise pH range just to keep you alive. The acid in your stomach is incredibly strong, around a pH of 1 to 3, to break down your food. But if the pH in your mouth drops just a little bit below 5.5, your teeth start to decay. And it's not just us. Acid rain can wipe out life in a lake. Even something as small as a bee sting, that's an acid. And what's the classic remedy? A mild base, like baking soda, to neutralize it. See? From our own bodies to a bee sting, pH is absolutely everywhere. And if you want to talk about extremes, get this. The atmosphere on Venus, it's made of thick clouds of sulfuric acid.
The whole planet is shrouded in it. It really puts into perspective how critical that delicate pH balance is for life here on Earth.
Okay, for our last section, let's pull all of this together. We know that when acids and bases cancel each other out, they make salts. But it turns out one of those salts is way, way more important than you probably realize. Yeah, I'm talking about the stuff you sprinkle on your fries, common table salt, sodium chloride. We think of it as just a seasoning, right? But in the chemical world, it's a giant. It's one of the most vital raw materials we have, the launch pad for a ton of other chemicals. Now, this diagram might look a little intimidating, but the process, called the chlor-alkali process, is actually pretty straightforward. You take salt water, brine, and you zap it with electricity. That's it. And that simple jolt of power is enough to break everything apart into 3 super useful chemicals. You get chlorine for things like bleach and cleaning supplies, you get hydrogen gas, which is a clean fuel, and you get sodium hydroxide, a really strong base that's used to make everything from soap to paper. So think about it like this. Starting with just that one ingredient, plain old salt, we can kick off this amazing chemical chain reaction. We can use it to make baking soda. Then we can take that baking soda, heat it up, and make washing soda for laundry. And remember that chlorine we got earlier? We can use that to make bleaching powder. It's like this whole chemical family tree, and the root of it all is just salt. Which kind of leaves us with a pretty cool final thought, doesn't it? We've seen how acids and bases battle it out, how we measure their strength, and how a single grain of salt is the key to a whole world of essential chemicals. It really makes you look around and wonder what other everyday things are hiding that kind of extraordinary potential, just waiting to be discovered.